Okay, everyone, let's start. I want to hear that high energy. Good afternoon, okay? Good afternoon, everyone. Very good. So next week is going to be fall break, which means that you're going to have a couple of days to do what? Assignment 2. You should have been done with assignment 2 already.
Attempt to implement GMM and bulk my head against the laptop when I'm unable to implement GMM.
He wants to do that. Please don't do it. So, quizzes. We're going to have a quiz this week, but what we're going to do because of the fall break, we had a discussion with our TAs and so on, so we're going to release it one day early, so which means it's going to be released today, so you can just get it done sooner, okay? The quizzes. And you don't bang your head on your laptop, please.
Not literally, but like figuratively.
Figuratively. So the other part, okay. Then after fall break, we're going to have a very important lecture, which is dimensionality reduction. Why it is important? Because it's, as I mentioned, it's a bridge between unsupervised and supervised learning. And today we're going to finish density estimation. The half part of density estimation, which is about parametric density, you already know it. So it's just about refreshing your mind about what we have learned so far. The second half is a part that is just kind of new for you, and we want to make sure that we understand what happens to the second part of this lecture. Any question? Any question before we start? Any concerns, any feedback? Nothing? How is homework 2? Which one is tougher, homework 2 or homework 1? Homework 2. You know, you were just thinking homework 1, like a lot of writing, and now you got homework 2. You're going to get homework 3. Like, that's a very beautiful gift. Homework 3. Okay, so going back here, let's start our density estimation. So before we start, let's have the meme of the day. Why do we love exponential term? Anyone? Any thoughts? Gaussian distribution, does it have an exponential term in it?
Yeah.
Yeah, so why do we love exponential term? Any ideas? Yes.
Take a log of it, and it might be concave.
Exponential is already convex, right? I think it's strictly convex. It's already good, but you're right. Log of exponential of u becomes what? U, right? Thank you, exponential. So you make things like a lot easier. What else? That's very important. So if I take the derivative of exponential, it becomes what? Becomes exponential. Nothing happens to it. As if something's there and doesn't do anything. Like a neutral member. So if you look at it here, when I take a derivative of exponential, what happens? Nothing happens. And we love this one in ML. Right? When I take optimizer, when we do optimizer and take a derivative, I want a term that doesn't hurt me, and exponential is one of those. Okay. So going back, we're going to talk about two parts, parametric and non-parametric. Okay. So what does it mean by density function? I'll talk about that. But before that, let's understand continuous variable and discrete variable. We already know it. We went over this in our second lecture. And the acronym for this one, the kind of shortened form, was PDF. And for discrete is PMF. I had another one, another kind of acronym, which was also PDF. What was that one? It was also a PDF. Probability? What is the difference between probability distribution function and probability density function? Density is used for just for continuous. Distribution is used for all of them, discrete, or just a general definition, right? It's a general definition. Okay. So area on the curve is equal to 1. Summation of all properties must be equal to 1 for discrete. So let's understand here what is happening and why I need to express and why I need to define a distribution or density function from my data points x here. So if you look at this graph, what type of distribution I'm using to explain this data set? We're using this one. What are we using here, this one? How many Gaussians? Anyone knows the name of this type of plot? We call them contour plots. Anything in middle means the high peak point. As I go to the sides, all these contours, which are to have the same values, all these contours on that elliptical shape, they have the same values. Then we'll go to the values, like a very low point, okay? So that one, what is it? What type of distribution I'm using here to explain my data, to represent my data? What's that? Pay attention. So how many Gaussian do you see here? So what is that mixture coming from? Yes, so it's a Gaussian. So am I using univariate Gaussian or multivariate Gaussian? Because I have more than one feature. It's a kind of 3D view, but contour plot shows like kind of the 2D structure. Okay, how many parameters do I have for this Gaussian? When I want to optimize it, how many parameters I need to optimize for a Gaussian? 3? What are those 3? But this one is just a Gaussian distribution. Just a multivariate Gaussian.
Just mu and sigma.
Exactly, just mu and sigma, because we are dealing with just one Gaussian, just one Gaussian. Okay, so how many parameters I need to optimize? 2. So how about the next one right now? Next one. What is next one? This one is our GMM. How many components I have? 2 components. For each component, how many parameters I need to optimize? 3, pi, mu, and sigma. So in total becomes? 3 for one of them, 3 for the other one becomes 6. Thank you so much. Okay, so these are called parametric. Why? Because I have parameters that I need to optimize. Okay, these are parametrics. And so what is the output of, so if I define Gaussian, Gaussian is a mathematical equation. And that's quite important for us. Many of these ML algorithms, I can't directly use X data points. I need to convert it into a mathematical explanation, mathematical form, so I can just put it into our ML. And then I can optimize that model. I cannot optimize X matrix, right? So we need to define a mathematical definition that represents that data so we can optimize it. So let's say here I use Gaussian to define that data points. Now from now on, I say that you Gaussian, you're representative of this data, so I need to optimize this Gaussian. Okay. And also having data, finding a distribution for your data, it can be very useful. Why? Because then once I have this distribution for my data, maybe wrong or right, but we assume that's right. If a data is outside of this point, let's say I have a data here, it tells us what for pre-processing? It can be a noise and outlier data point, right? They can help us with cleaning our data set. Okay. So many reasons that we want to define a Gaussian, not Gaussian, density function for our data. So what I have here, I have 2 histograms, very important visualization and very important method. By the way, this one is non-parametric. I'll talk about this. This is one of the very powerful one out there to understand what happens to your features in your project. Like, let's say you have a data set that has 20 features, 30 features. You want to understand how each feature is being distributed. In fact, it's very important for your project. You can plot all these histograms for every single feature. if they follow kind of similar distribution, this means that there's something learnable about your data. Visually, you can see something learnable. Okay, this one, can I call this one a PDF, by the way? Anyone, can I call this one a PDF? Why not? What's that?
Probability distribution function.
Proud distribution function.
Yeah, no, that's discrete.
So that's a good point. Histogram can be used for both continuous and discrete. And I'm going to tell you that this one is continuous because linear algebra can be any number. So this one is for continuous. That was a good point? Yes.
It's not, because it's not a probability, the area under the curve is not.
The area on the curve is not equal to 1. What do I have? What do you see these values? What do we call them? We call them frequencies. I need to convert these into, this one is continuous. So what do we call them for a continuous? What do you call it? We call them, they are like to the density value. Right, so we need to convert it into density. And I'll just tell you how we can do it and so on. Okay, so we have for a statistic, we have for linear algebra. What do you think is going to be the distribution for our ML class at the end of the course? Which one?
All A's.
This way? You wish.
I do.
You do wish? Okay, so typically it's like that.
Oh.
No, no, okay, no, you're right. Typically it's like this, but it takes a lot of effort. You know, you have a lot of homeworks, project, and so on. So I'm not sure what is the name of this distribution, by the way. What's that?
Distribution?
Is it? Okay, or ML distribution, maybe, if we can call it that way. Okay, well, this is it. But again, it's not guaranteed that we're going to have this one again. Oh, that's up to you. Fall break, you know. Okay, so the other thing I'm doing here, linear algebra, statistics score, what I did, I put them together. This is also very good comparative study. What I'm doing, I'm comparing one feature against the other one. What is the benefit of coming up with such graph? It will tell us about what? Exactly, the relationship of one feature against the other feature. Do you think the relationship is positive here? Yes, because if one of them increases, if you have a good statistical score, this means that you're going to get a good. So what happens to this person who has a good statistical score but bad linear algebra?
Outlier.
Outlier. Something's happening over there. Something fishy, or maybe the student has been sick, or like a couple of things. So you need to look into it. So now you can understand why these are important, because then you can investigate what is happening there. Okay. Any question? For your project, again, comparing features against the other feature can be quite helpful. So you can understand what are the relationship between different features. Okay, so parametric, again, means that we have parameters like Gaussian distribution, Bernoulli, which is used for discrete. This one is used for continuous. Here I'm using univariate or multivariate. So instead of variance, I'm using, what is the size of our covariance is d by d. Remember, covariance is d by d. These notations are quite important. Our mu becomes a scalar or a vector for multivariate Gaussian. Mu becomes a vector. Good? Good, everyone? Okay. And then I'm going to talk about non-parametric histogram and kernel? No, not density. Kernel? Come on, you forgot. Anytime I say kernel, you should say something after that. No. Kernel, you need to say something after. It was like second lecture or third lecture. Kernel, you should say what after that? Not Jupyter Notebook. Come on. Anytime kernel happens, what happens after that? Yes. There you go. Kernel? Sliding. Everyone repeat. Kernel? Sliding. Kernel? So some sort of sliding is going to happen. But here we're going to have some sort of mathematical sliding. Okay, don't forget this one, because we're going to use a lot of these kernels in like CNN, deep learning, and so on. So there are a lot of sliding happening over there. Okay. So histogram kernel, these are non-parametric density estimation. We'll talk about those. Non-parametric doesn't mean that we don't have any parameters. One might say that we have a lot of actually parameters. That's what we call it that way. Okay, so here I have a multivariate Gaussian, and I'm using a parametric model. And here I'm using KDE, kernel density estimation. So you can see that it can capture local information way better than one Gaussian. Right, so how it can capture all of this kind of information and so on, we'll get to know that one. Okay. Yes. What's that?
Are you doing kernel density estimator versus GMM?
This one is what? This one is GMM or not? This one is not GMM. But do you think I can come up with another parametric model that can replicate whatever I have in kernel density? Like what?
Could you say it's the sum of like multiple Gaussians?
So if I have two Gaussian here, possibly these two Gaussians can replicate whatever I have here, possibly. So if I have two Gaussians, this model becomes what? GMM. So if I have GMM, maybe GMM can behave quite similar to kernel density estimation. But there is a problem with GMM. How many parameters do I need to optimize for two components?
6.
It's going to be very time consuming. I'm going to tell you, you can just calculate the whole thing for this in one shot. Way, way faster. Okay? So there are reasons that we want to do this. And also, if I tweak the parameters a little bit here, I can capture even more local information. I can have hundreds of these Gaussian and calculate it in just one shot, in one for loop. Quite fast. Okay? So, any question here? Good? So this one is our contour plot. When I say contour plot, if this value, I'm just going to give you the number, is 10. What's going to be this value? 10. All of them are 10, right? They have the same. That's why we call it contour plot. Okay? And this is for Gaussian. This is for our KDE, standing for kernel density estimator. Okay. So let me, before I go here. Gaussian distribution, how many parameters we have?
We have 2.
Thank you. So what are those? Let's say we're talking about univariate. Mu and sigma. What is kind of a compact form I can write it here? X given? Theta. What is the lazy form?
X.
That's a lazy form. Okay? So all of them are acceptable. Again, depending on the context. Okay, so mu and sigma. Remember I mentioned that it can be A and B. How did they realize that mu becomes A and sigma, sorry, A becomes mu and B becomes sigma? How did they do it? What approach I took so I could understand that why one parameter is mu and the other one is sigma, why one of them is average, the other one is variance or standard deviation. What we did, we went through maximum likelihood estimation, right? So the first thing I did, I created what? I created a likelihood function. Anyone remembers how I created likelihood function? When we created likelihood function, do we do it for one data point or all the data points?
All the data points.
We do it for all data points. So if I have it here, let's say this one is my data point 1, data point 2, and data point n. So what we need to do, this becomes my, what do I call this? This is our likelihood function. Okay, and then I need to maximize this. What is the problem here? If I want to maximize this, what do I have? No, I have a joint probability. Is it easy to optimize a joint probability? Anytime you see joint probability, you need to think of other ways to convert it into a simpler form. So for this likelihood function, in order to maximize it, what was the assumption we had?
It's our IID.
Exactly, the data points are independent of each other, which naturally happens. Student 1 is independent of student 2 and so on. So if it's IID, how can I write it? F of x given theta multiplied by of x2 theta, and the last one? Theta. So what is f of x1 given theta? This value, right? What is f of x2? This one. And what do we do with all these vertical lines? We multiply them together and we maximize it. Okay, we multiply them together and maximize it. So if I want to write it in shortened form, this becomes I from 1 to n, f of xi. This is our likelihood function, and we need to maximize it. What is the problem with this form, though?
It gets very small very fast.
It's the density values are quite small values. When I multiply a bunch of a small value, it becomes even smaller. So vanishing happens. Vanishing happens. So how can I avoid this vanishing problem? We take the log, so multiplication becomes addition. So I need to take a log of this. Are we clear? Are we good? So we have been working on this multiple times, so we should be good by now. Okay. So that's why I have this one here, log of I from 1 to n. This is our likelihood function. Take the log. Okay, let's do it for one discrete and one continuous. This is the equation of what? What distribution? This is our Bernoulli. Let's say this one is head, this one is tail. One drawback with this type of writing, Bernoulli has this problem that it goes into two directions. In fact, the original equation is like this. It goes through to two directions, and that can be problematic when it comes to optimization. It's hard to optimize an equation that has the shape of like this. So people have been smart, and they just combine this equation into these two roots into one, and they created this one-liner equation. In fact, these two are the same. Why? If I put x equals 0, represents 1 minus theta. If I put x equals 1, becomes theta. So now I have a one-liner equation, so I can optimize it much easier. Okay, so that's something that people typically do. If they have something like this, they convert it into one-liner. Okay. So now that I have this log of likelihood function, I from 1 to n, this is our PDF. This is our PDF. I put it here, and when I just multiply theta, multiply theta x1, multiply theta x2, and so on, they have the same base. And what do I do with the power? We sum them up, right? We sum up the power. That's why I can see NH here. We already did this in our class. NT, I'm going to write it as NT is equal to total number minus NH. Log of A multiply B becomes what? Log A plus log B. I have one parameter, theta. Take the derivative with respect to theta. By the way, I'm using lowercase l, which represents log likelihood. Okay, so theta becomes number of heads divided by total number. So we had this example. Now let's do it for a continuous case, Gaussian distribution. I have two parameters, mu and sigma. Okay, so I'm using univariate here or multivariate? Because we are using variance here, not covariance. Okay, so y mu becomes average, and y sigma square becomes variance. Why is that? And I'm going to say because we maximize the likelihood. Because we maximize the likelihood, that's why we get this. In fact, when people say that mu and sigma are equal to these values, this means that this equation already has been optimized. And we already given the optimized one. So we should not just take it for granted. Someone already optimized this for us. So that's why we have it. OK. So how do I do it? This is for one single data point. If I have n data point, becomes multiplication of all these n data points. And I take the log because of the log likelihood. OK. So this multiplication of, this one is a constant term, is being repeated n times. And log of multiplication becomes log of addition. So if this one repeated n times, that's why I have n here. So n of this constant becomes n of the constant, right? It will be repeated n times. So what is log of 1? 0. I didn't write it here. I'm going to write this one as a and b. This one is log of a and b. What is log of a and b is equal to log of a minus log of b. So you can see that log of a, negative value, log of b. How do I have sigma squared here? Where did I get the sigma squared? I have sigma here. How did I turn it into sigma squared? I mean, what I did is just to simplify things. Do you think these two terms are the same? Yes, and that's what I did. I just like replaced it with this term because they're going to have the same kind of multiplier to make it easier. So I have two parameters, mu and sigma squared, and we need to take the derivative. So typically I do change a variable. When I have like a crazy variable, I just do a change of variable, make it u, so it's easier for us to take a derivative. If you want to, this is one approach you can take. Okay, let's do it with respect to mu. Not going to go into details. This one doesn't depend on mu, becomes 0. Doesn't depend on mu, becomes 0. And then here depends on mu. So there is a negative sign here, multiple negative become positive. And then we have this value. Once I get mu out of this, mu becomes what? Mu is equal to? What do I call this? It's our average, our mean, okay? So if I do it with respect to sigma squared, so this one is 0, log of, what is the gradient of log of u with respect to log of, with respect to u? 1 over u. And that's why here this log of sigma squared becomes 1 over sigma squared. And then you do the same, kind of the same behavior here, equals 0, and this becomes our sigma squared. What is this equation? This is our variance. And now you can see that why sigma squared and mu are equal to those values, because these are the result of what? Maximizing the likelihood function. Okay, any question? Any question? Good, we're good, okay. So this is the result, Gaussian density. This one is in the 3D view, and this one is a contour plot, and so on. Okay. So far, we already knew most of these materials, and from now on, it's just going to be new, especially second part of non-parametric. And so where we're going to use non-parametric for visualization, we're going to see it in this lecture. We're going to use it in classification, regression. We're going to see it in future as well. Okay. So let's go back to histogram. What was the issue with this graph?
Not probability.
It's not. So it's not a PDF, right? So I need to convert frequency into?
Likelihood.
Yeah, so because the class is density estimation, let's call it density. Okay, so density or likelihood. So let's call it density. Okay. So for this, I'm going to prove it to you, or I'm going to show it to you how we're going to convert this frequency into density. Okay. I'm going to give you an example. Example is not difficult. Let's say I have data points, just one feature. Let's say height, just one feature. And the values are between 0 and 1. Just again, it makes it simple so I can prove it to you how it works. I have n of those data points, and I'm going to create m bins. These are the number of bins. If I have m bins, what's going to be the bin width then? What is the bin width here? Upper bound minus lower bound, what is that value? How about here? 1 over n, so the bin width is 1 over n. Why is 1 over n? Because again, our case is between 0 and 1. And this is our bin 1, bin 2, bin L, and bin m. C means count. Well, for us, count is same as frequency, right? So this becomes what? This becomes count 1 means what? The number of data points within that bin. So this becomes count what? The number of data points within second bin. And the number of data points within last bin, bin m. Okay, in fact, the frequency values. Good? Okay. And I'm going to say that in order to convert those into density value, those frequencies, you got to follow this equation. Like, accept it blindly for now from me, and I'm going to prove it to you why we follow this equation. So essentially, this is the number of bins. This one is total number of data points. And this one represents, let's say, if L is equal to 1. If L is equal to 1, what it does, so it will count all the data points. It says whether xi belongs to bin 1 or not. If it belongs to bin 1, it will assign 1. Otherwise, it will assign 0. So if I sum up all the data points, sum up a bunch of ones belonging to bin 1, that means what for us? So I find the number of data points within that bin, and for each data point, like, do you belong? 1. Plus, do you belong to that bin? Plus another 1. Do you belong to that bin? Plus another. Do you belong? No, 0. When you sum up all these ones, it becomes what? The number of data points in that bin. So essentially, we represent C value for us. For instance, C1. So this is what for us? This one is C1. Well, I'll put 1 here. I'll just put an example here. So if I want to put this one into words, essentially this is our number of points in bin L, or our C, total number of data points multiplied by bin width. Okay, we don't know how it works, why this is the case. I'll show it to you. But let's say assume this one is really a density and this one is really a PDF. What do you expect this value to be? If this one is a PDF, which means y1 because? y1 because it's a PDF. So D, what is equal to 1 in PDF? The area on the curve is equal to 1. So this must be equal to 1 if this is a PDF. Okay, so let me show it to you how I got to this equation. Let me give you an example. Let's say I have bin 1 here. I have second bin here. And I have third bin here. Okay, so this one's count 1. This is our frequency. This is our X data. This is on count 2. This one is our count 3. A question. Count 1 plus count 2 plus count 3 is equal to what? Total, which is n. Total number of data points. So now, what do you think is probability of bin 1?
Probability or C1 over n.
C1?
Over n.
C1 over total number of data points that bin over the whole data points, right? C1 over n. Okay, are we good? What I'm using here, I'm using frequency. Let's say I did something magically and converted this one into the same data, converted into density. Same data. I'm going to call this one density. Okay. Then 1. Then 2, and then 3. So this is our F1, density for the first one, density for the second one, and density for the third one. And let's say this one is A, B, C, and D. What is B minus A? This is our what? This is our bin. Based on the previous slide, what was our bin width? One was 1 over L. Okay. How do I calculate probability if I have density? How do I calculate probability in bin 1? Give you an example. What is the probability at this one X? What is the probability at X? Continuous variable is 0. So how can I calculate probability in a continuous variable? We need to have a range. So I need to define a range here. X plus T, let's say. Okay, now I can calculate. I calculate the area. I can calculate the probability. What is our range here? First bin. A to B. So how do you calculate the area on the curve? Becomes what? B minus A times F1. Okay, what is B minus A? 1 over M multiply F1. Are these the same, PB1, PB1?
Yes.
Okay, the same. I'm going to equate them here, which means C1 over N is equal to what? 1 over M, F1. So this means that F1 is equal to what? C1 divided down by N multiply 1 over M. So if I go back to this equation, C divided down by total number of data points multiplied by bin width. So we can see how we got to this point. Are we good? Any question here? Okay, so I also need to prove it to you why the area on the curve is equal to 1. Okay, let's do it. So that was the equation of PDF that we had. That was the PDF equation. So what I'm going to do, this integral, instead of just doing integral for the whole PDF, I'm going to divide it into for each bin. So integral over the first bin, second bin, and all of that. So essentially, if I compact all of them, it's going to give me this integral that I have in the So what do you think is this summation here for the first bin? All the data points belonging to that bin. This will give us what? This will give us what? C2, and this one? C3, no, C, there's 3 dots. It was M? Yes, M, that's one. So can I rewrite it in this form?
Yes.
I'm going to write in this form, and let me collapse it together and just write it in terms of summation. So I'm summing up and writing it this way. So in fact, if I put L equals 1, will give me the first one, L2, second one, and so on. So how do I do this integral here? What is integral of a constant multiplied d of x? Becomes what? Constant multiplied by x. D of x becomes x here for us, which is integral. What do I do? Upper bound minus lower bound. So if I do upper bound minus lower bound, L goes away, and then because C of L. So what is C1 plus C2 plus Cm divided down by N? This becomes N becomes 1, right? So the area on the curve is equal to 1. So this is how we can prove it. Good? Any question here? Yes. Good. Is it clear? Like 100% or 95? 100%. No, over there. Do not respond on his behalf. So 95 or 100? 95. So tell me that 5%. It's okay. Am I putting you on the spot? That's okay. So we can talk about that later. Anytime that comes to your mind, let me know. Any other question? Any other question or any question? No, no question. No. Okay. So, well, histogram is we love histogram in machine learning because it is fast. It's very fast and quick. But it also comes with some problems. So let's say I'm going to go from one-dimensional to two-dimensional. If I have 10 bins in one-dimensional, the number of bins are going to grow what? Exponentially. Like if I have 10, in two-dimension, it becomes 100. So you can see that it grows exponentially. One other issue. So for this data points that I have here has one feature. I'm going to start the bin width from number 2, the integer number 2, and then I have this kind of histogram here. How many peak points I have here? How many peak points do you see? How many? If I just smooth it out, how many peak points you see? You see one peak point, right? For the same data, let's see what happens. For the same data, I'm going to start bin width from 1.75. It becomes like this. Now how many peak points do you see? Now we see 2. So you can see that histogram can be a little bit problematic when we have limited data, right? So we're going to have these gaps, so they're going to be creating problems for us. Okay. For this reason, we're going to talk about something. Everyone, pay attention to this part. That's a very important part of a lecture. This is the last one. For this reason, we're going to learn kernel. There you go. Density estimator. Okay. So let's see what happens here. So I'm going to ask you to accept this one blindly, that this one is a PDF. And I'm going to show it to you later on. But for now, just let's understand what's happening in this equation. Okay, n is the number of data points. H is, we call them bandwidth. It's not bandwidth, it's called bandwidth. Bandwidth. This one is our grid line. What is it? We don't know. Grid line. And this one is our data point I. Data point I. One single data point. Okay? And this term here, this is a normalizer. This is a normalization constant. Normalization constant. Why we have this term here? Because we want to make sure that the area on the curve becomes equal to 1. That's why it is necessary and required to have this term. Okay. In practice, people write this P of x in this way, 1 over n sigma 1 over h k u. Ku. So u is equal to what then? U is equal to xl minus x sub I divided by h. Okay. So this k is a function. This k can be any function, but any function that you can come up with, by the way. So I'm going to give you a couple of examples of the functions that we love to use in terms of k. But any function that you want to come up with, it must satisfy these conditions. Otherwise, they're not going to be acceptable function. You can come up with your own customized one. I'm going to show you one example that we typically use. It's called Gaussian kernel. Okay? So it behaves like a Gaussian. In fact, this one looks like something like this, a Gaussian function. And I'm going to tell you this bandwidth, if I put it in the Gaussian kernel context, it behaves like what? So if I put u here, it becomes what? xl, xi, h. What do you think this one behaves like what? Yes?
I just had a question.
Yes.
So the output of the Gaussian kernel function, would it be the same as the Gaussian we saw for the contour map? really early on.
It's going to be very similar, yes. And we're going to see how it works actually. Yes, it's going to give you density value. You're right. Okay. If I replace this value here, if you look at it from Gaussian perspective, H represents what? In Gaussian distribution, what did I have in the denominator? Sigma squared, right? So H squared, sigma squared. So bandwidth behaves very similar to sigma. So if bandwidth is high, this means what type of Gaussian I have? This type of narrow Gaussian or the wide Gaussian? Wide Gaussian. So if the H is a very small value, I'm going to have a very narrow Gaussian. The other thing about the Gaussian, the tails of Gaussian go to what? Infinity. That can be problematic a little bit because it's going to be computationally expensive for us because the tail will go, I'll tell you what, why this is problematic for us, because this goes to infinity. Okay, so I'm going to mention a couple of more functions before I go into details what is really happening here in this function, okay? So a couple of other kernel functions. Gaussian, the tail will go to what? Infinity. On the other side, people define the other type of kernel, what they call them top hat. What is the difference between top hat and Gaussian? Yeah, but what is the, why we want to go from Gaussian to top hat? What was the issue with Gaussian? It goes to infinity, but top hat has what? A bound, minimum, and that can be quite helpful. What is the problem with this part of this top hat? These corners, we call them sharp corners. Once we have sharp corners, means what? Suddenly the value changes from very large value to very small value. Anytime that you have sharp corners, it will create kind of like a peak point, like a peak structure in your plot, right? Because we are introducing some sharp changes. And so, but on the other side, Gaussian, which one is going to be smoother, Gaussian or top hat, the end result? Gaussian, because it's not sharp, like going from a high value to low value suddenly. That's why people combined these two together and created what? What's that? No, this one is called what? You're saying something just for saying it? I've been trying to say this one for like multiple years now.
How do you say it?
I don't know. That's what I'm asking you. Yes.
Epanashnikov.
She should it be there? Epanashnikov? No, I'm not close. You don't, he doesn't even know. Then you just
I have no idea.
Oh boy. Okay, so whatever the function is, it's a good function. Why? Because it's combining, it's getting the good word from what? From both of them, right? And we have it here. The other one is exponential, the other one is linear, and this one is cosine. If it's hard for you to pronounce this one, so you can use the cosine one. It's quite close, but this one has a kind of a sharper slope here. Okay. So we're going to go understand like how this density estimation works. Like essentially, this sliding is going to happen and so on. Okay. So if I have h, it's a very small value. When h is a small value, we're going to come up with a narrow Gaussian or wide Gaussian. Narrow Gaussian. This means that our Gaussians are focusing locally on data points. So I'm getting a lot of peaks, right? So as soon as I increase the bandwidth, it becomes much wider Gaussian. At the end, my KDE behaves like what? Behaves like this one, the result, the KDE result. Behaves like a Gaussian. So I'm better off using just one Gaussian. Okay, behaves like a Gaussian. So the question becomes, what is a good value for h? Or we called it bandwidth. What's the good value for bandwidth? Okay. So I have 50 data. Let me give you an example. With this example, we'll understand what happens here. I have 50 data points. I'm going to run histogram on top of these. Here it is. Are we happy with this result? Not really because of why? Not really. There is a huge gap here. So who is going to represent this data here?
Probability is 0.
We're going to see it. We're going to use KD to represent this. OK. Now I'm going to apply KD. In order to apply KD, you need to divide your range, your area, into, they call them linear spaced lines. OK. Or we call them grid lines. These are our grid lines. So I had 50 data points. This is a rule of thumb. This is not kind of like a set stone rule. If you have 50 data points, possibly you need 4 or 5 times more than your data points to create grid lines. Let's say if I have 50 data points, 4 multiplied by 50 becomes 200. 200 grid lines would be a good representation of your data points. And when I create, anyone, have you heard of linspace in NumPy or MATLAB? Linspace, it's a library. Linearly spaced. So this one, these are linearly spaced lines, which means that the horizontal distance of one from the other one is equal to each other, all of them. These are all linearly spaced, the same value. OK. The minimum value of this is around this, I don't know, any number here. But where did I start my grid line, the first one? What value I use? If you can see it. I'm using negative 15. Why I did it? Again, you got to start from some safe range. You should not start from exactly your minimum point. You got to start from a safe range when you started. You got to also end it with a safe range beyond your maximum value or beyond your minimum value. OK. Any questions so far? No question. So what I'm going to do, I'm going to drop a Gaussian kernel here. This is our Gaussian kernel. And I'm going to start from the first grid line. I'm going to start it from first one. I'm going to go to the second one. Going to go to third one. What is this process? Sliding. So you can see that sliding happens, and I go to the last one. So we are sliding this function. It's a kernel sliding. So let's see what happens in every slide. So let's do it for the first one. Okay. What happens here? What is the red one is the x value of our grid line. Let's say x of the grid line L, this one that you see here, x of L for the first one. What is the value? What is the x value of the grid line for the first one? Where did I start it? What is the x value? So I dropped it on negative 15. Where did you get 0? You were looking at what? OK. No, there is no counts here. It's just, OK. So we start from negative 15. What I need to calculate, I need to calculate U's here. And I's is for number of data points. So I can do it for data point 1, data point 2. What is the last data point? How many do I have? 50 of them. OK, once I calculate this, I also need to calculate this one. So KU1, and the last one is? KU50. OK, let's do it for U1. U1 means what? And let me assume that H is equal to 1, bandwidth. Just a very simple example here. OK, H is equal to 1. OK, U1 means what? What is our X? What is our grid line X value? Negative 15. What is the X of the first data point here?
Probably like negative 12.
Negative? Sure, let's do negative 12. So this becomes plus 12 divided down by 1. So this becomes negative 3. And then I need to, this one in fact is a normalizer that I divided down by 1. So in fact, U's that I have here, these are the horizontal distance, the normalized one, from each data point to our grid line, right? So I need to calculate for all of them. So what is KU? If I put KU1, so it becomes what? How can I calculate it? 1 over 2 pi E negative divided by over 2. Okay. So what is this one? In fact, KU1 will give you this vertical line, the density. Remember that we mentioned? The density value for this Gaussian kernel. So we'll give you this value. So KU2 will give us what? Second one. KU3, do I need to calculate KUs for these two? Why? Because the tail of Gaussian will go to? And that's the problem, right? So why do I need to care about those? Because the tail will go to infinity. I need to calculate all these vertical lines. Once h is equal to 1, by the way, here, so it doesn't count here. Once I calculate all those vertical lines, what does it mean by this operation? So I sum up all these vertical lines and take the average, and will give me just one scalar. Whatever I have, I replace it over there. So that scalar. So the next one, I move it to the second line, third line, and so on. So then I'm going to have all these points. Okay, when I connect these dots together, I will get something like this. Right? So why do you think this value is quite low, around 0? If I drop this around 0, what's going to be the KUs for this? Are it going to be a small value or large values? Small. The average of small values become quite small. So that's why the value is quite small here. Okay. Any question about this part? Yes.
Where did we get 12 from in?
12?
There we go, -12.
So the x of the first data point is -12. Michael said -12. That's on you. Okay. He said 12, -12. So that's why we just mentioned -12. Okay. Okay. Any other question? Okay. So I can also write the whole thing that I did in a matrix form. So what I did here, this is 200 by 50, so 50 data points and 200 grid lines. So essentially for 0 here means we're talking about grid line 0. So you can see that the values are quite small. The values are quite small, and we take the average. Okay. This interactive example is quite interesting. Let's look at it here. Okay. So, normal. What do you think happens if I reduce the bandwidth? Am I going to have more peaks or going to have less peaks? So we're going to have a narrower Gaussian or wider Gaussian?
Narrower.
If we have a narrower Gaussian, which means that it's going to focus more on local data. So if we reduce it, you can see that the blue one, we're getting a lot of peak points. So if I increase it, what's going to happen? Smoother, right? So you can see that if I increase it a lot, it becomes almost behaves like just one single Gaussian. What's going to happen if I'm using triangular? Do you think it's going to be more kind of rugged, or like it'll have a lot of peak points, or it's going to be smoother? Yeah. So you can see it here. If I reduce it, you can see that these are more kind of dominant. That the way that these peak points are here, if I compare it with Gaussian with the same number, this will produce a lot of more sharp peak points. Okay, or peak, I don't know, the structure that we have there. Any questions here? Yes.
How would Epineshnikov behave here?
Thank you for mentioning it. There you go. You can see that it's smoother, right? So let's compare it with this one, triangular. This becomes much smoother because of, again, the function that we have. And if I increase it, Okay. Going back. So that becomes our end result. This becomes our end result using KDE. Okay. Now I'm going to show you one example. Yes.
Just a parabola, or what exactly is this?
The triangular.
The Epineshnikov.
So that one, the top hat.
No,
The Epineshnikov.
the Epineshnikov,
Oh.
the one that's like this.
So what is it? It's a cone shape.
What's the function of that?
What is
What's the function? Here. You're so interested in that, huh? Here's the function.
parabola?
Yeah. It's very close to that. It's negative x squared, right? So symmetrical is quite important. All of them are symmetrical because you want to make sure it's unbiased for the left and right data points. Okay, so I'm going to use MATLAB here as our pseudocode. Anyone knows MATLAB? Oh, if you're a CS major, don't talk about MATLAB. That was good. I liked it. Okay, but let's just give it some slack here. Okay, so just use MATLAB. Okay, so what I'm doing, I'm generating 200 data points, and the minimum value is negative 13. The maximum is 13. I'm kind of cheating here because I generated those data points using the Gaussian distribution, 2 different Gaussians. One of them with a mean value of negative 10, mean value of 10. In order to calculate the bandwidth, everyone, you got to use this equation. It's called Silverman's rule of thumb. What is this one? This one is essentially our standard deviation. So you can calculate the standard deviation of your data, so you can calculate your bandwidth. So first thing first, I'm going to use this function, linspace, to create what? To create our grid lines. And I'm starting from negative 25. Why negative 25? The minimum was negative 13. Because we got to start from a safe range, well beyond the minimum and well beyond the maximum. I'm using 1,000 grid lines, a multiplier of what of data points? I have 200 data points, 5 times more than my data points, so that it could be a good number. Okay, so let's look at the true PDF. This is our true PDF. Okay, and let's see how KDE can represent this one. Let's compare GMM with KDE. This is just KDE. Just 4 lines, you can do KDE. GMM, you're going through that pain already. How long it's going to take and so on. So let's see how it works. We're going to start from the first grid line, again, sliding. Starting from first grid line, and this becomes our first grid line minus a vector, all the data points. Scalar minus a vector becomes what? Becomes a vector. What in NumPy or MATLAB, it uses what? Broadcasting. So this becomes 200 by 1, for instance. So what it does, this horizontal distance, remember horizontal distance from all data points from the grid line, it does it in one shot. So I have all the U's. And then once I put them in KU, and this one is also going to be 200. What are these ones? These are the vertical lines. These are the vertical lines. I use the normalizer, 1 over h, and then I calculate the average of all these vertical lines. It's going to give me one number. I put it for the first grid line. I do it for the second grid line, third one. So then, if I have all these lines, grid lines, for the first one, second one, third one, then any question? Any question? Okay. So this one is our P of X. You can see it's a good representative of our true PDF. It can capture the peak points for us. I mean, the trend follows the same structure. Value may not. I mean, I can just scale them up and down, so just be the same thing. But as long as the trend follows the same structure, so we should be happy. Okay. From 1, 2, and 3, are we increasing bandwidth going from 1 or decreasing bandwidth? When we decrease bandwidth, we're going to capture more local information. It's going to have a lot of peak points because we're capturing we're paying more attention to local. Here is more generic. Okay. So for H, we're going to use Silverman's rule of thumb. And it's a better method, KD, for in terms of computation. If you compare GMM, if I have 3 Gaussian, I need to optimize 9 parameters. If I have 100 Gaussian, how many parameters I need to optimize? 300. But here is just one for loop. That's it for us. It's just for us need to define H and the number of grid lines. Okay, any question? Any question? Yes. Well, in this scenario, I can't just avoid for loop. Okay, why do you put me in this situation right now? In this situation, we need to have for loop. Okay, yes.
You don't talk about for loop, what about while loops?
That's a black hole. So you may not just get out of that one. While loop is just very bad, worse than for loop. Okay, today is about KD. It's not about while loop and for loop. Are we done? Are we good? You ready to leave? Okay, I'll see you next week, everyone.